Oh, good morning, friends. We'll look into the fifth numerical on steam nozzles. In a steam nozzle, the steam expands from 4 bar to 1 bar. The initial velocity is 50 meters per second and the initial temperature is 200 degrees centigrade. Determine the exit velocity of steam if the nozzle efficiency is 95%. So, the given conditions are at the inlet P1 is equal to 4 bar, T1 is equal to 200 degrees centigrade, velocity is 50 meters per second, V1. At the exit, steam pressure is 1 bar, P2 is equal to 1 bar, nozzle efficiency is 0.95. So, given the conditions are given, inlet and exit, straight away we will take the Moller diagram. We can plot points 1 and 2 on the Moller diagram. So, you can see this Moller diagram. This is a constant, this is saturation line, and here you have got the pressures written. So, this is a 4 bar line 1, and this is a 1 bar line, constant pressure line. So the point for the point 1, we will take inlet condition 4 bar constant pressure line, and then we will see the constant temperature line 200 degrees centigrade where it intersects. So the intersection point 1, this becomes the H1, and from here we will straight away drop a line straight isentropic line to the which will cut the point 1 bar line at point 2. This becomes H2, and because it is having only 95% efficiency, so this H2 dash is a uh, actual enthalpy drop due to the friction and 95% efficiency. Okay. From the steam tables, you can straight away get these conditions from what we are supposed to find out is velocity at the exit V2. From steam table also you can find out enthalpy 1 is 2860 kilojoules per kg and entropy is 7.171. Okay. The exit steam is having 1 bar pressure. Here we don't know the condition, means the dryness fraction of the steam. So what we will do, we will find the HF2 and HFG2. Okay, HF2 is 417 and HFG is 2257 kilojoules per kg. We will use this relationship S1 is equal to S2. Okay. And from the steam table itself, SF2 is equal to 1.3 and SFG2 is equal to 6.057. Using this relationship, we will try to find out the dryness fraction. S1 is equal to S2 is mixture of fluid plus wet region. So SF2 plus X2 into SFG2. So substituting the values SF2 as 1.3 and SFG2 as 6.057, we will get the value of X2 is equal to 0.969. So please understand the dryness fraction should always be less than 1. It can be anywhere 0.8, 0.9, but always less than 1. Okay. Then enthalpy also, now we know the dryness fraction, we know the enthalpy of the fluid as well as the latent heat. So we will find out the enthalpy 2, that is HF2 plus X2 into HFG2. Okay, HF2 is 417, X2 is now known 0.969 and HFG is 2259. So this enthalpy 2 at the exit is 2605. Okay. The enthalpy drop should be H1 minus H2, that is 2860 minus 2605, that is 255 kilojoules per kg. But given the condition that the efficiency of the nozzle is 95%, we will multiply this enthalpy drop by 0.95. So we will get the actual enthalpy drop. This is the isentropic enthalpy drop, but the actual enthalpy drop is 95% of that is 242 kilojoules per kg. Now to find out the exit velocity, we will use the standard relationship. Okay, so delta H enthalpy drop is equal to V2 square minus V1 square divided by 2. Okay, and this delta H is 242 now actual enthalpy drop. We will multiply this by 1000. Please remember this you have to multiply by 1000. In the actual equation we use 44.72 square root of delta H. So that 44.72 is nothing but this 2 into 1000, 2000. This square root of 2000 is 44.72. Okay. So V2 square minus V1 square, that is 50 square.